Welcome back, guys. Today's video is going to be covering polarity and dipoles. Now, before we worry about polarity or drawing a dipole for a molecule, we need to make sure we have the correct Lewis structure drawn for that given molecule. If you need a refresher on drawing Lewis structures, make sure to check out my channel. I have a video going through step-by-step how to draw a Lewis structure. Now, let's look at this Lewis structure for HCl. It's drawn correctly, so now we can talk about polarity and dipoles for this molecule. Now, first, breaking down polarity. Now, when I think about polarity, I think about the electron cloud. Now, what is the electron cloud? We can picture the electron cloud as this cloud of electrons surrounding every molecule, right? However, on this molecule, we are going to have differences in electronegativity. Now, electronegativity tells us how much that particular atom wants the electron cloud. Now, if we look at HCl, chlorine is much more electronegative than hydrogen. So, in reality, the electron cloud is not drawn so symmetrical here. So what we're going to have to do is say chlorine is going to get more of that electron cloud. Now, it's a bit dramatic. However, just to show, chlorine is much more electronegative, so it gets more of that electron cloud. So what does that have to do with polarity? So polarity is going to tell us that there is an uneven distribution of the electron cloud due to a difference in electronegativity, right? There's this big electronegativity difference, so we have this shift of the electron cloud. When you have a situation like this, you can now say that you're working with a polar bond, right? Polarity is talking about that difference in electronegativity resulting in a shift in that electron cloud, right? So we can call this a polar bond. Now, the question you'll often be asked is this molecule polar? Now, we cannot just say that the molecule is polar because it has a polar bond. We need to actually deal with something called dipoles. So, what are dipoles? Well, dipoles are vectors, right? Let's make sure that we know that they're vectors. So dipoles are vectors. Now, in order to draw the dipole for this molecule, what we're going to do is we're going to draw an arrow from the more electronegative atom to the less electronegative atom, okay? So we're going to draw the arrow just like this, right? You can draw this little line here. So this is the dipole for this molecule, right? You draw it from the more electronegative atom to the less electronegative atom. Now, if we're going to answer the question of is this molecule polar, we need to keep one more thing in mind, right? So far we've said, yes, we have polar bonds because we have this difference in electronegativity. The electron cloud has shifted, right? So we have our polarity. We do have a dipole, right? So in order for you to say the molecule is polar, you need to have an overall dipole. Now the thing you need to keep in mind is vectors can cancel each other out. So if you have a molecule where you're drawing dipoles due to your polar bonds and the dipoles cancel out, you're actually going to have a non-polar molecule. So you need to have an overall dipole that's not canceled out if you're going to call that a polar molecule. So now that we've gone through polarity and dipoles, let's take a look at some of these practice problems. So it says, consider the molecule CF4. Does it have polar bonds and is it polar? So let's erase our HCl, right? And let's draw our CF4 molecule. So CF4 is going to look like this. And each fluorine is going to have 3 lone pairs. So we've successfully drawn our Lewis structure out. And it's asking us, does it have polar bonds, right? And when you ask the question of, does it have polar bonds, what you're asking is there a difference in electronegativity great enough to make it so we have a shift in the electron cloud towards one atom, right? And fluorine, being the most electronegative atom on the table, is much more electronegative than carbon. So if we think about it, if we just zoom in on this bond right here, we'd expect this electron cloud to be greatly in fluorine's favor. However, let's make sure we draw our dipoles before we say that this molecule is polar or not, right? So back to our practice questions, not to get ahead of ourselves. Does it have polar bonds? It definitely has polar bonds, right? Because these bonds between carbon and fluorine are definitely going to be polar bonds. There's this big difference in electronegativity between the two atoms. However, you can't say it's polar until you've drawn out the dipoles. So let's draw out the dipoles here. So you draw it from the more electronegative atom to the less electronegative atom, right? So we're going to draw it from fluorine to carbon, fluorine to carbon, fluorine to carbon, and fluorine to carbon. Okay, so remember, these are vectors, right? And if we add up all of these vectors, we're actually going to see that they cancel out. So the way I like to think about it is picture carbon is a book on a table, right? And you have 4 people surrounding this book, I should say, right? And each person is going to push the book in a different direction. So you have 2 people pushing forwards and backwards, and 2 people pushing from side to side. Now, even though you have 4 people pushing on that book, it's not going to go anywhere, right? So just because we have polar bonds does not mean this is a polar molecule, because the individual dipoles cancel out and there's actually no overall dipole. So remember, in order to say that a molecule is polar, you need to have an overall dipole, not just polar bonds individually. So no, this is not a polar molecule. We'd say that this is non-polar. So now let's go down to number 2. Are the following molecules polar? So our first example is HF. So let's draw HF. So we have the Lewis structure here. Okay, now in order to determine whether this is polar, let's think about it. Do we have polarity here? Well, we do, because we have fluorine, which is much more electronegative than this hydrogen atom. So if we think about the electron cloud, what we're going to see here is fluorine get much more of that electron cloud than hydrogen, right? So we have polar bonds. That's our first step in determining if we have a polar molecule. Now let's see about the dipoles. So we're going to draw this dipole from fluorine to hydrogen, right? It's the more electronegative atom to the less electronegative atom. Now, we don't have any other dipoles to cancel this one out. So yes, this represents our overall dipole. So yes, this is a polar molecule. So we have HF completed. Let's tackle NH3. So we have N. Get a better marker here. So we have N, H, 3. And we have this lone pair. Okay? Now, it's important to note, the reason why I didn't draw these hydrogens in a symmetrical fashion, right, surrounding the nitrogen, is because this lone pair is made up of electrons. This covalent bond and this covalent bond are also made up of electrons. And remember, negatively charged things repel. So the electrons here and the electrons here are going to repel each other to make it have this shape, right? So it's important that you know that when you're dealing with a molecule with a lone pair, it's going to have some repulsion, and you might have a polar molecule when in fact you didn't expect it to be polar because you thought it was symmetrical, right? So this is not going to be symmetrical. We're going to have this lone pair repelling, making these hydrogens, sit at this angle with the nitrogen, right? So do we have a polar molecule here? Well, we definitely have polar bonds, right? We have nitrogen, which is more electronegative than hydrogen, right? So we're going to have 3 polar bonds. Now, let's draw our dipoles. So our dipole is going to be going from the more electronegative atom to the less electronegative atom in each case. So, do we have a polar molecule? Well, these 2 dipoles will cancel out, right? These 2 right here will cancel out. However, we have this overall dipole that we can see right here going down. So our overall dipole is going down. We have polar bonds. This is a polar molecule. So let's do our last example of H2O. So far we've said that HF is polar and H3 is polar. Now let's draw out water. Now for water, we have O, right? And we have H2. And again, the two lone pairs here are going to repel these electrons. So we're not going to see something like this. If you drew it like this, you'd actually be incorrect, right? So we're actually going to draw it like this with that repulsion going on between those electrons. And with enough practice with Lewis structures, you will get the hang of this. So let's see if we have polar bonds. Well, oxygen is much more electronegative than hydrogen, right? And polarity is talking about that difference in electronegativity. And we can now say that because oxygen is much more electronegative than hydrogen, this is a polar bond. Now, is there dipoles? Now, we're going to draw the dipoles here and here, right? From the more electronegative atom to the less electronegative atom. Now, again, these are vectors, so we can add them up. So if we have one going this way and one going this way, the overall dipole will actually be going straight down. So back to our example, if we had people pushing something, right? If we have one person pushing it this way and one person pushing it this way, it's actually going to add up to go straight forward, right? So that's going to be our overall dipole, and we can say that all three of these molecules, I should say, are polar. So draw your Lewis structure, determine whether there's polar bonds due to that difference in electronegativity, draw out your dipoles from the more electronegative atom to the less electronegative atom. Make sure when you add them up as vector quantities, they don't cancel out. At that point, you can say you have a polar molecule. So thanks for watching, and make sure to check out more videos on the channel.